we figured out how you make the X-rays from our X-ray light bulb or X-ray tube. And then once we have these X-rays labeled here called incident photons, we basically have two major ways of those X-rays interacting with matter or with the patient. Okay. The photoelectric effect, in which the X-ray knocks an electron off of the atom. It's called the photoelectron. And then you can have characteristic radiation come out of that atom, or you can have an Auger electron come out. They're both, as an electron drops down from a higher orbit down into the place from which the photoelectron was ejected, energy comes out of the system either as characteristic radiation as a photon or an Auger electron. Both of those get lumped in as photoelectric effect. Compton scattering is the other major way that the incident X-rays that we've created get absorbed or deflected by the patient. Many of these, they undergo a scattering with the scattering angle is not, say, 45 degrees or 90 degrees, such that it totally exits the patient. It's a smaller angle at which the Compton photon that results from this interaction of our incident photon comes close to an electron and sort of reflects off of it at some angle. And then as that Compton photon travels to our detector, one hopes that it's at a sufficient angle that it hits what's called the anti-scatter grid and gets absorbed, right? Yes, question.
So doesn't the anode fire electron, not photon?
Oh, what are we talking about here now? The anode?
Yeah,
Oh, okay. Are we going back to the X-ray tube?
like totally different.
Yeah, this is different. So remember, we did two interactions with matter. We've just recently done two. The first one was we boil electrons off of a cathode and accelerate them towards a target, which is the anode. And that collision creates these X-rays that we've labeled here as incident photon. Okay. So the diagram looks the same because it's an electron hitting matter and there's some kind of collision and scatter and things like that. Once that's done and we have a beam of X-rays coming out of our target, then we look at this. And so these atoms are actually in the patient, right? So they're part of the target, and we're going to cast a shadow. And the shadow will be, an X-ray shadow. So, yeah.
Sorry, the characteristic radiation in the first graph, is it a photon too?
Yes. The characteristic radiation is a photon. Okay. And what are the relative probabilities of these two events occurring? These formulas give those probabilities, or the cross-sectional probability. So if I have an incident X-ray creating a photoelectron with a photoelectric effect, this goes as the fourth power of the atomic number of the atom. And that's because we have more and more electrons. As the atomic number goes up, the cloud of electrons that the photons can interact with goes up, and increases the probability of this happening by a large factor with atomic number, power 4. It also, this type of interaction, the probability of it occurring decreases quite significantly with energy. So as the energy of the incident X-ray goes up, the amount or the percentage, say, of interactions that are photoelectric, or the probability of this occurring, goes down precipitously. Okay. And for the Compton interaction, where we just reflect or have an interaction with an electron and come off with a Compton photon and an ejected electron, this is how the probability of that changes. It too goes up with atomic number, sort of density of electrons in the sample or the patient, but not as quickly, right? And the interesting thing, it's relatively constant with energy. Okay, so regardless of the energy of this X-ray, the probability of having a Compton event is about the same. And we can look at a graph that shows this is the mass attenuation coefficient, probably in water. Does it say here? Yeah. And it's the component of that attenuation that is produced by either the photoelectric effect or the Compton effect. So a high mass attenuation coefficient means a lot of X-rays get absorbed. A low mass attenuation coefficient means the X-rays pass through more easily. And we are interested in X-rays that have an energy here between, say, 20 keV and 120 or 140 keV. Somewhere in that range is what we're interested in for X-ray imaging. This is 1 MeV. So this is up here is like gamma rays up here, right? So we actually have pair production occurring here with a photon that has this much energy. You can actually make an electron and a positron spontaneously, like matter. That photon can turn into matter, right? So if you have enough energy up here. But we're interested in these X-rays between, say, 30 keV and 140 keV, something like that. If we look at the photoelectric curve, we see at very low energies a very high amount of X-ray absorption or a large mass attenuation coefficient, right? And then across the range of energies that we deal with in X-ray imaging, that changes by decades. As you can see, it's changing. This is a log scale. So it's a factor of 10. Here's a factor of 100, a factor of 1,000, right? So it is dropping precipitously with energy. This curve gives the probability or the mass attenuation coefficient from purely Compton scattering. And as you can see, over our energy range, it is pretty constant. Okay. So that's just happening all the time for all energies at 30 keV to 120 keV. Interestingly, this gives us an opportunity, right? If we could make an image, let's make 2 images of the patient. We'll make one image, say, at 40 keV. We'll use electrons that are at this energy. Well, we're going to get this much photoelectric effect, right, from that beam, and this much Compton. And now we crank up the energy, take another image right away of the same patient at, say, 140 keV, and now we have virtually no photoelectric effect, but we still have the same amount of Compton. So now we have 2 images that are quite different, right? So one image is basically a Compton scatter image, and one is a photoelectric plus Compton image, right? So with those 2 images, I now can create a synthetic image that is some kind of combination of those two to bring out different contrast in different tissues. Recall that, I think we'll probably look at it right now, different tissues have different mass attenuation coefficients. Okay, that's how we have the contrast between them. So let's review our system that we've got here. We have a source of X-rays, and this is that cathode boiling off electrons, hitting an anode target, creating a beam of X-rays. It actually creates X-rays in all directions, but we're just going to allow them to exit this box through this hole. Okay, so they're all just coming out here. Ideally, all of the X-rays would emanate from a single mathematical point, so that when I came down here, I know exactly from where that X-ray came from, exactly. Unfortunately, we would burn up our target if we did that. So it usually comes from a rectangle, right? And so that adds to a bit of blurring on the imaging because the X-ray might have come from over here, or it could have come from over here, right? So there's a bit of blur. Yeah, question?
Question about 2 slides ago about the X-ray interaction with matter.
Okay.
So I was wondering, it says on the screen that Compton scattering dominates at high or low atomic numbers, but it seems like the atomic number at the top is proportional to the amount of Compton scattering happening.
Uh, well, that so at low atomic numbers, it's saying Compton scattering. Let's where are we reading this? I'm sorry.
Sorry,
Right here? I see. Not much contrast. Oh, okay. Yeah, because here, with this effect here, that you would have the probability of a interaction occurring at z to the fourth with photoelectric. So as the atomic number gets bigger, this probability gets very, very high, right, compared to the Compton. That's what that's saying. Right, right.
The top thing is not having like much of an effect on the actual probability because it's not being like to the fourth power is like
Right. Well, the ratio, just the amount of photoelectric events that would occur for a low atomic number thing versus Compton, and then you go to a high atomic number thing, and the photoelectric is going to take off and be the dominant event. Don't get that confused with the energy here, right? That's just the energy of the photon, not the Z of the actual element, right? We'll get to a chart where we have different Z's, actually different elements. Okay.
For another question regarding the energy, it's the first effect is proportional to the inverse of the energy to the power 3, right? Something like that.
Yeah.
Which means with higher frequency, we get less of photoelectric effect.
Correct. Correct.
Why? Like, isn't it like if I imagine a more frequent way, is it
Yeah.
more probable to impact? Why does that happen?
That's a great question. Why this is mu to the third power? I do not know. Like is my answer to that question. Why it would go as to the third power? I'll look it up.
Why is it inverse inverse proportional? Why isn't it like just proportional to the frequency?
Right.
When I increase the frequency,
I don't know. I'm going to say I don't know to all those because these two formula, I don't know the derivation of that formula, but that would be where we'd find out that answer. We can look at the derivation of these two formulas and try and figure it out. All right. Sorry. Don't know. Yeah.
20 and 100. But the area just before that also has like a greater photoelectric effect.
Yes. Because if you get down there, the problem about making images down there is none of them get out of your sample. So that you shoot these, say we put 10 keV photons into the sample, nothing's coming out. So your image will always be the same, right? So you have to have enough penetration to have some of the photons survive, right? Ideally, large like 50% of them would survive or something like that. Yeah. Well, it's because as you saw, different materials have different amounts of photoelectric effect based on their Z number. And so you can make a photoelectric effect image and you can make a Compton image, right? So basically your photoelectric effect probably is a Z image, right? Okay, cool. So we've got our small rectangle, ideally a spot, but it's not. We filter out the X-ray photons that are below a threshold energy because they're just going to get dumped in the patient and not produce any contrast. And so now we have a beam of X-rays coming down here and they hit the patient here. They get differentially absorbed on their pathway through the patient, right? And if there's bone in the way, they're going to get absorbed more than if there isn't, etc. And then goes through the tabletop. This is the anti-scatter grid, okay? So that if my photon comes through here and it has a Compton interaction and then shoots off this way, when it hits the anti-scatter grid, it will be absorbed. It won't cause a flash down here in my detector. So let's say I move through the patient, I survive my travels through the patient, I get through the anti-scatter grid, I hit this stuff, and this is a screen. It's usually some kind of phosphor screen that lights up when X-rays interact with the material in it, causes a flash. And in the old days, this just used to be a piece of photographic film. And that flash would cause a chemical reaction in there, just like taking a photograph, right? Yeah.
Filtering the X-rays again?
It's to get rid of the low energy X-rays that would have no chance of getting out of the patient.
Okay.
So they would all just dump into the patient and none of them would get through.
So they would get absorbed and then you would be able to see like
They don't cause any contrast. All they cause is dose, right? So they just get rid of them. And you can, oftentimes the filter is aluminum or copper, but depending on what you use, you will change the energy spectrum of your beam, right? So you could weight your energy spectrum to high energies or lower energies. So that, yeah. It actually, here it's not a big deal. I mean, wires absorb X-rays very well, so they show up as very bright objects in the image. They will generate artifact in CT because they absorb so much of the X-rays. You oftentimes, behind a device like that, you will get no X-rays hitting the detector. And so as you do your projections, it becomes a very dominant structure. But for the most part, you can get around those problems. Unlike magnetic resonance, where you have huge RF energy in the field and electronics in a pacemaker. And so those two things sometimes do not mix, right? You have to have a specially designed pacemaker so that it's not sensitive to the radio frequency energy. And it doesn't have ferromagnetic materials in it. Okay, so we're going to write down some equations to look at these concepts. The intensity that we're going to detect on our detector. This will go up if we have more X-rays and down if we have less. The intensity, it's going to be proportional to the photon fluence. That means how many photons are coming at the detector. Remember, I can dial up my current on my X-ray tube and just make more photons come through. That would change this term, the photon fluence. And it's proportional to the energy. So higher energy X-rays, when they hit the target, will make a bigger intensity, a bigger splash, right? And in terms of the photon fluence, it's usually given in number of photons per unit time per unit area. Okay, those are the units of the photon fluence. And so we've been talking a lot about the energy of the X-rays that we are shooting through the patient. Let's say we set our voltage on our X-ray tube to 100 kilovolts. That means the highest energy X-ray I can have coming out of that tube is 100 keV, kilo electron volts, right? Because it's an electron accelerating through there. And so that's the highest energy I can have. And then this is the relative number of photons at all the other energies between that and zero. Okay, so it's just if you know what a probability density function is, this is like that. It's essentially, the ratio of photons. And you can see this has a sort of a peak somewhere around 50 keV, something like that, right? In order to get the entire fluence, we can integrate all of the photons coming out at all energies. So this curve we're going to call S as a function of E, right? It's the relative numbers. And I can just integrate under that curve to get the total number of photons per unit time, per unit area coming out of my tube. So then I multiply that by energy and I get an intensity, right? And it's just how many X-rays at this energy are coming through is governed by the probability density function, or this density function SE. So I just integrate under that probability density function times the energy, and that gives me my intensity. Okay.
Right.
It also gives you the mean value of this.
Maybe it's a dumb question, but why isn't it one the area under the curve if it's a probability thing?
Well, we can set it to 1. Sure, I can set but here's the deal. So if I set this one to 1, okay, so if I do my integral, I just have some unit and I say that's 1. Then I crank my kilovolts to this. Now, do I set this to 1? Right? The big one? Probably not. I want that to be 1.4 or something, right? So their relative numbers depend. But it is, if you wanted to say, hey, let's set everything such that at 100 keV, this thing is going to integrate out to 1, then we could do it that way. It's kind of arbitrary in a way. Yeah.
Why is it that if you increase the X-ray photon energy past a certain point, the relative X-ray intensity goes down?
If I increase the photon energy, I'm going this way, right? You're saying, oh, as I go this way, why does this go down?
Yeah, because it goes up for a bit and then it goes
Right.
down.
Right. Oh, okay. Good question. The actual question is, why does it go down on this side? Right. So if it's just the probability of a Compton interaction at 120 keV is very small. When I put my tube to 120, I do get some photons that have like complete elastic, like 180-degree collisions with electrons, but not many. Most of those collisions are at angles that shoot the Compton photon off at a smaller angle, right? And the relative probability of those would just keep going up linearly, just like this, right? Unless we filtered out these low guys. So when you filter out the low guys, then the curve looks like this. If it was just pure physics and the relative probability of these different Compton interactions at different angles, it just goes up as a straight line. Okay.
Perfect.
Yeah, I mean, basically we'll see most of the time you just assume you're imaging with an energy that's kind of the mean value of this thing at 50 or 60 keV, right? And then you do all your physics based on that. We'll see that. Okay, so let's look at the attenuation, how you model it. This is a very heuristic explanation. It's very simple. If I have, say, 1,000 photons and they hit a target that's like 2 centimeters or maybe a centimeter of water, and what comes out the back end of this, what emerges from this thickness, this 1 centimeter of water, is 800 photons. 200 of them got absorbed, right? And then if I have this 800 photons now coming out and they hit the same dimension target, 1 centimeter of water, say, then again, I reduce this by 20%, 640 photons come out. If I do it again, 1 centimeter, 640, I take 20% of those out in interactions, 512 come out. So you can kind of see how this is going, right? And if we plotted that along this curve, that function is simply whatever the starting number of photons is multiplied by an exponential decay, right? That is linearly proportional to however long the distance is we've gone through times this thing called the linear attenuation coefficient. And that linear attenuation coefficient is particular to whatever is inside this target. If it's water, it has a certain value. If it's air, it has a different value. If it's bone, it has a different value. Okay. So you can imagine with bone, I'd lose more than 20% of my photons through this, and this curve would be steeper. It would be a faster decaying exponential. Okay. So that's the concept of linear attenuation coefficient. The reason it's called linear is because if you look at it explained this way, if I have big N photons hitting my target, and my target is some delta X, then the number emerging from the target is just mu times big N times delta X. Yeah.
coefficients, you said it depends on the object and we target it. So so is it possible to, like how we determine like the coefficients?
Oh, you measure them.
So is that like digestible?
Nope. It's like water is water. And so if I put water in a scanner and I put x-rays through it and I measure how many x-rays come out the back, I can measure mu.
Arbitrary.
It's not arbitrary, it's just whatever God did, you know. That's right. It's like that's water. And then you have, aluminum and copper and all that stuff they're empirical numbers. You could maybe derive them from first principles, but doubtful, right? And so basically there's a table it's called the National Institute of Standards and Technology, and they have books, now electronic books, that give all of these values for all different materials, right? And then if you're making a phantom, say you've got some resin that you're printing with and you make a 3D phantom, then you usually get the resin and make a nice little sample and shoot x-rays through it and see what its mu value is, right? It's a very prescient question. A CT image, in the end, when you put up a brightness map and you say, this is my CT image, it is a map of the mu values. That's what it is, right? It's linearly scaled, but it's linearly proportional to the mu values of what's in the sample. So we're going to make pictures of this thing, right, with CT. So when you set up the equation like this is why it's called a linear attenuation coefficient, right? It's a very simple relationship here. And from this equation, you can just derive, using a simple first order differential equation like you've done 1,000 times for a beer warming up to room temperature or whatever, you get this equation and this is the solution. So you have a couple of things. You've got how many photons you start with going into the sample, right? And then the number that come out the back of the sample is proportional to the number you start with, e to the minus mu delta x, which is the thickness of the sample. And mu values, it turns out, you'll see, we'll show you a couple of them, and they're hard to remember, right? Because they're like 0.69134 or something like that for water, right? So an easier thing to remember is the half value layer. And so most people that work in X-ray imaging or CT know the half value layer for lots of different materials like water and muscle and lung and brain and all that kind of stuff. And so the half value layer, very simple concept, right? It's what is the delta X value I have to put here in order to create half of my photons being absorbed, okay? And so it basically is just mu, or the half value layer is 0.693 divided by mu, okay? It's easier to remember. So here's some example half value layers. And so after doing this, you will know kind of how things are going on in your patient in terms of how many photons are left, right? So let's look at the half value layer for muscle. It's going to be different for different energies, right? At low energies, 50% of the photons are gone by the time we've gone 1.8 centimeters into the patient or into the muscle, okay? So that's not that far, right? It's that much, right? So when I go in 2 centimeters, 50% of the photons are already gone, right? And then 4 centimeters, 50% more are gone, right? So it goes like that. So that's down at 30 keV. When we get up to 150 keV, you have to go close to 5 centimeters through muscle to drop by 50%. But still, that's, giving us photons coming out the back of the patient, which is a reasonable number. Bone, on the other hand, you don't have to go far at all. It's less than half a centimeter at 30, but it's 3 centimeters at 150. So this is a graph of the energy and the half value layers. And you can see that as the energy goes up, it takes more sample to attenuate the object. This is why when you have a really big patient who comes in the scanner and they're a large person, 300-pound person, and you put them on the table, you usually crank the energy up to 120 keV just to get the photons through, right? Because otherwise you don't get enough on the detector, right? Yeah. Well, yes, and that's what creates contrast in images, right?
I would just assume maybe the bones have a different distribution efficient.
They can. That's absolutely right. So you could say if I wanted to make very precise measurements of the mu value inside this patient of the actually cortical bone, it's probably most susceptible to changes in density of that bone. And so you could model, say, look, I can make bone density measurements by looking at the actual values that I'm getting here. And other than patients' overall size is the most important factor when deciding what energy you're going to scan at. Because as the patient gets bigger and bigger, you usually scan at higher and higher energies such that more photons get through. Okay. Okay. And remember when we're talking about contrast, I said there's a simple way of doing contrast. You take signal A on some object, signal B on another object, take the signal A minus signal B, divide by the standard deviation, and that gives you your contrast, right? And it's in units of standard deviation, right? So you're saying, oh, I've got 5 sigma contrast between these two things, right? In X-ray imaging, because the intensity is proportional to this equation, right? It makes sense to do this local contrast measurement where you take, if this is A, right, I get some signal A and I get some signal B and say, well, what's the difference between these two signals, right? We could do it that straight up way, but another way of doing it is say A minus B divided by your original A and ask what's the relative change in the number of photons that hit over here versus here. So you take A minus B divided by A, just plug all that in, and you get this, which is very simple, right? So basically the contrast from A to B is just 1 minus whatever this little delta mu z is here, right? So it could be like 0.95 or something like that if z was really, really small. It gives you a percentage change in the signal intensity relative to the background, right? So this is used in CT quite often. So let's look at attenuation of X-rays along a path through the patient. This is where things get really interesting because it's not just a single type of tissue that our X-ray is going to go through at this point. It gets to sample a whole bunch of tissues on its path through the patient, right? So we'll say we have a source up here and there's a beam of X-rays coming through the patient along this line, and it's going to hit our detector down here, okay? So we're just focused on what's happening along this beam, right? And at any point, right, inside there, the incident number, the rate of change of number divided by the incident number along here is proportional to whatever the mu value is at that location, right, times delta x. So if you think about this, let's not think of it continuously, discretely. This is some delta x, some little unit of distance in the patient. I have a mu value across that unit. We'll say it's constant across that small unit. This is the equation that governs how many photons I lose in my pathway delta x through the patient, right? So I'm going to lose some, and then I move to my next delta x. I'm going to lose some more. I move to my next delta x. I'm going to lose some more. And the number I lose is going to be linearly proportional to whatever the mu value is at that point as I'm going through the patient, right? So if we take a look at our mu values as we're going through, if I come through here, and this tissue right here is muscle in the chest, then all my mu values along here are muscle. Then I might have to go through bone. I might hit a rib right here. So the mu value will change as the x-rays go through there. Now I'm in the lung, which is essentially air with a bit of soft tissue in it. So the mu value again changes a lot as it drops. So I don't attenuate many photons as I'm coming through here. I hit a vessel, might have contrast in it. Mu value goes up. So that's the deal. That's my pathway, right? And to figure out the number of photons that come out the back and are going to get hit or hit my detector, it's the sum of all of those processes, right? So basically, the number that come out the back of the patient are the number that went in the front, right? Integrated across all of these mu values, right? So I integrate that function that is mu as a function of distance along this line. And that's going to tell me my final attenuation number, right? If I want to do it, this is assuming that we've just picked an energy and we have mu for those tissues at that energy, right? However, remember the beam has many different energies in it. And so I really should compute this function for each of those energies, right? And then we would calculate what the intensity is, because I would remember the bigger energy ones would give a bigger flash and such. So to incorporate that, I have to know what the mu value is as a function of energy. So now I've got a tissue, let's say here we said that this was muscle in the chest wall. I need to know mu as a function of energy for muscle. And so I know that. And I need to know the beam that came out of my X-ray tube. I want to know the relative probability density of each energy. And then do this whole integral that involves integrating over all of those energies, right? That's a pain in the neck, right? And in fact, it's very hard to do it absolutely correctly because it's really hard to know this function for one thing, right? The manufacturer will not give it to you. You have to go in and try and measure it. There's a nice project, okay, for this is like design an experiment that you could run on a clinical scanner that, and I'll give you a hint, you would scan different materials, right? And you calculate what is this function from those measurements, right? It's kind of a neat little project, okay? But suppose we don't know. We know it's a blob, like the ones that I showed you. They all look kind of like that, but you would need to fit, you would go back here. It looks something like this, right? So you would need to break it up into like, I don't know, 8 chunks and then measure how big it is in each chunk and then fit a sensible curve to that, right? It's kind of a cool project. Okay, so this is the intensity I get on my detector for, this X-ray pulse. So the mass attenuation coefficients for some materials, here we go, and it shows you the difference. These attenuation coefficients are normalized to density. Okay, they're density normalized. So you want them basically such that if I had air and then I compressed it such that it was really dense, right? You don't want the attenuation coefficient in your table, right? You want to be able to use that same attenuation coefficient. So it's normally normalized to density. So here's the relative numbers, right? At 20 keV and 100 keV. And you can see why it's easier to remember half value layers because these things, you're not going to remember all these numbers, right? And so here we have different materials and the linear attenuation coefficient of those materials as a function of photon energy. So here's bone, right? Everything goes down in terms of linear attenuation coefficient as the energy goes up, but they go down at slightly different rates, right? And so contrast between bone and muscle and fat, right, are slightly different here at 50 keV than they are over here at 80, okay? But for the most part, when we're calculating or doing a simulation or reconstructing an image, we basically say we know that we have photons, between say 50 and 100 here, but we're just going to assume that all of our photons are at the mean at 60, and we'll do the math accordingly, right? As opposed to trying to do it in multiple dimensions, with energy being one of those dimensions. It does lead to some artifacts, which we will take up. Here's the addition. So here's our basic tissues, and this is the addition of a couple of new curves, which are contrast agents, okay? So remember, contrast agents have really high attenuation, linear attenuation coefficients. So they absorb a lot of X-rays. That's why they're here. So this is hypake, which is the stuff you inject in vessels to do angiograms. This is barium sulfate, which is what that guy was swallowing in the introductory lecture. And both of these have a thing called a K-edge. And so you have a linear attenuation coefficient, and then it suddenly changes when you cross a certain energy. And in this case, it's 33.2 keV. And what this means is the photons, once they're above that energy, they have enough energy to knock out a K-shell electron. They need that much energy to get that job done. If they don't have that much energy, that will never happen. And so once you get above that energy, you can start knocking K-shell electrons out. And so the linear attenuation coefficient changes for the material, right? Given that energy. And so that's called a K-edge. And this is the K-edge of barium is 37 keV. Here's an image of that stuff in the gut when you're looking for untoward geometries and things like that in the gut. This is, do I go back to, yeah, here we go. So this is the liquid contrast agent that we're going to put in the vessels, and you can see it attenuates X-rays. Great. Here is an angiogram in the brain of a patient, and they've injected contrast and taken this picture. And the interesting thing here is that, as you can see, all of the background attenuation seems to be gone. And the reason that is they've obtained two pictures very close together in time. They first take one picture below the K-edge and one picture above the K-edge of this contrast agent. And so once they're above the K-edge, they get a very high contrast in the vascular structures. But anything that isn't this contrast agent looks exactly the same for those two energies. So you just subtract those two pictures, and all you have left essentially are the vessels. And it's called DSA, or digital subtraction angiography, and it's used a lot to image brains, specifically if you're looking for aneurysms and things like that. And so that's using the physics of this K-edge to get super high contrast. Okay, so what we're going to look at now is how you detect the X-ray once it's exited your patient. Okay, yeah.
Does the K value depend on the material which is being scanned?
Yes, yes, it does. So the question is, does this position of this K-edge depend on the material you are scanning? And yes. So you would design it so this probably has a K-edge that's associated with iodine. This is probably associated with the barium, this K-edge here, right?
For a bone, we'll have a different K than for
You know, I'm not sure, but it doesn't look like bone has a K edge on this graph, right? Looks like it's pretty smooth all the way down. So these are very pure ions, or that we're imaging.
Tissues like hydrocarbon that don't have that.
I don't think so, no. It's particular to a certain atom. Yep.
The subtraction image you showed,
Yep.
that's kind of inverse what we normally see, isn't it? Like the higher contrast, the higher absorb things that absorb more
Yep.
photons are
Yep.
normally white, right?
Yep. So
Great.
it's a good point. And if this was MRI, those vessels would be white. But digital subtraction angiography over the years, they just looked at them in this orientation and just kept doing it, I think. So it was just the preference of the radiologist. You can imagine just doing the subtraction the other way, But I don't know why they look at it black. Probably because neuroradiologists, when they were doing angiograms in the brain without DSA, were just looking at the raw data, right? And probably they just looked at the dark vessels, right? And so once you've looked at 10,000 in one orientation, your brain has kind of trained to see things, right? We essentially are, we're deep learning units. Like you just do it over and over and over again. And who knows how your brain does it, but really good radiologists, they'll look at something and they'll just see an abnormality right away before the rest of us have to scan through and go, oh, look at that thing. Okay, so what we're going to look at is the difference between a modern version of detecting X-ray photons that come out the back of the patient. So in order to measure this shadow, we need to have differential signals on our detector. And the things we're detecting are photons coming out the back. Ideally, these photons have traveled a straight path from the target, right? Or from the electron target from our source in our X-ray light bulb. They've traveled a straight path from there to our detector, right? Straight back up. And when we get a flash, we say, oh, one made it through, right? And in 99.99% of CT scanners that are out there right now, what happens is the X-rays come in and they cause a flash in some material. And there's a lot of designs of these materials such that the flash is very bright or the flash is very short-lived, etc. And so that light flash is contained inside a little square detector, and you have mirrored elements on the wall so that the light stays inside that one detector that you've caused the flash in. You don't want it to leak out to the neighboring detectors. So these sepia between the active elements basically isolate and make the flash stay inside. That obviously reduces your efficiency a little bit because you're sacrificing material to cause an interaction with the photon with these mirrors, right? So you got to put them in there. The efficiency of these things, like if an X-ray photon comes through and hits this detector, the efficiency is pretty high, but it's not perfect. It's not 100%, right? So there's still a yield that comes. I can't remember precisely what it is right now. And so when we get a flash, then you have a photodiode here that just reacts to light and gives you a voltage that's proportional to the light. And that's the detector. Okay. So you can imagine these things are going bling, 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 right? And all these signals are coming out that are proportional to the brightness of those detections. A new way of detecting X-rays. It's not that new, actually. It's pretty old, but it's just starting to become available in clinical scanners, is direct photon counting, as opposed
Excuse me, Professor? I think you're muted. Sorry, I think you're muted.
All right, can you hear me now?
Yeah, thank you.
All right, perfect. And you can see everything okay?
Yeah.
All right, terrific. All right, let's go back here. Thanks. So we get a splash of electrons. These are actually electrical anodes. They're just electrical conducting material that the electrons will bind to, right? And give you a pulse that is proportional to each single X-ray photon. So it comes through, creates a number of electrons, creates more if it's higher energy photon than lower energy. So it's proportional. The number of photons created is proportional to its energy. And then you get a direct signal for that. And it's very local to where this occurs. Okay. And so interestingly, if we can make this happen, we now don't need septa, right? Because we don't have to contain light or anything like that. The electrons just get made and then they go straight to the anode. So we have a much more efficient setup that way. The other really cool part about this is that above this, you can actually make this anti-scatter grid less. There's less demand to have an amazing anti-scatter grid because those photons that have large angle deflection that would get hit by a normal anti-scatter grid, when they hit this stuff, because they've had this collision that puts them on a larger angle, their energy is lower. So you can filter a lot of those out just through energy, right? Excuse me. Um, the downside to this is the physics of this system has a certain upper limit in number of photons that it can detect per unit time. So if you overwhelm it such that there's many simultaneous photons being detected, you will get what's called charge pileup. Just like many photons come in, cause a lot of electrons, and they pile up on the anode, and you lose the ability to see distinct individual photons and count them, right? So you have to keep the flux to a certain level that you don't get this charge pileup, okay? This is oftentimes people do this as a project in that look at the different physical structure of those two detectors and how that would change scanning resolution, etc., signal to noise, stuff like that. Here's a classic detector, where we have here these scintillators, and then below the scintillator we have the photodiodes, and these are on chips. Basically, it's like a 32 by 16 chip or something that they all just plug in. And on this detector, this is one unit that's been pulled out. This is the Z direction. So you have essentially 256 independent slices being sampled simultaneously, because this is the Z direction. And then through, you would have a whole set of these things plugged in to make a detector. Do I have a picture of it? No, I don't. Darn. We'll look at this. We'll probably look at this a bit later, or you can look at this video down here. It has an exploding version of this thing, and it shows all the component parts. But this is the anti-scatter grid. You can see it's pretty severe, right? If I look up from a single point on my detector up through the grid, I can only see a very select direction, right? And it goes back to the target, okay? And so that's what the mechanics of a normal detector look like. And this is the detector here. And so the thing we just looked at was one slice of this. This is the Z direction and 256. And then this theta direction is about 1,000 pixels that way. We'll look at this in greater detail when we do CT hardware. And this is the X-ray tube and a big unit here to create high voltage. Okay, any questions on that? Yeah.
Photon counting also like use beam X-ray.
Yeah, sure. It can be. Um, the That's a great question. Just like a normal fluoroscope or something like that. It's not common, but I don't see why it shouldn't be, other than cost, right? So um, right now making these detectors and everything like that, because they're new, they're fairly expensive to make. But I'm sure those costs will come down, right? Okay. Any other questions on X-ray physics? All right, great. So we're going to, in the next 25 minutes or so, change topics and start looking at linear systems and some of the math that's sort of required to analyze images. Um, so a digital image, okay? We're going to start pretty simple here. We've got an X direction, a Y direction, and then each pixel in this function here has an amplitude, right? So let's say it's 0 in the background here. It's 500 there and 1,000 over here, brightness. And so point by point, we have different amplitudes across this picture, right? And you can have a three-dimensional array of pixels and take out one slice and it might look like this, and it can be a whole stack. So you can have a 3D object that has brightness as a function of position in the matrix. Often MR is 256 by 256, 512 by 512 on those orders. CT is 512 by 512 usually. So that's our function. We want to think of this thing as f of xy, right? Or as we'll see down the line, it'll be g of xy. This is our functional representation of the image. Okay, so mathematically, it's a amplitude as a function of position in the plane. So what are we going to look at here? There's three important things going on in this little diagram. One is how to characterize what the input will be to our imaging system, right? The other important thing is, what do we characterize as the output from the imaging system? And so here we have input, we're going to characterize as a function f, output is g, and then how do we characterize what our imaging system is doing by describing mathematically what it does to this signal to produce this image, right? So there's physics and sort of linear systems slash digital signal processing involved in this part here, right? And the two big systems we have here, we have a CT scanner or an MR scanner. So mathematically, if we'll see, we're going to call, if we make a really small dot over here, and we can call that an impulse. And if we send that impulse into our system, then what we look at is perhaps some blurry version of the impulse, or in this case, it looks like a sombrero function with wings of the impulse. We're going to characterize that as the point spread function. Okay, there's a whole bunch more variables here than we previously looked at, but don't panic. We'll get there. Let's do a quick review. In CT, if I put a tiny little metal bead in my CT scanner and take a picture, in just one dimension, if I'm looking at one dimension, it comes out with some function that I can characterize. Normally, I write down something like a Gaussian, and then I have an analytical description of what a bead will look like in my images. And that's also called the impulse response function, because this signal here is essentially a point or an impulse. Okay. In order to describe an impulse mathematically, we're going to use something called a delta function. How many people know what a delta function is? Okay, that's pretty good. And so a delta function is a very steep, it's like a point. Let's do it in one dimension. If I roll along the x-axis, and then at some point my amplitude fires off to a very high number, rolls along just a little bit and comes back down. So I have a very narrow top hat function. Okay, so we can all picture that function, right? Let's cut the width in half of that top hat function. We'll just make it even thinner, and we'll make it twice as high. Okay, so now I've got this really tall thing, and it's quite thin. So why don't we do that again? We'll just cut it in half and make it twice as high again, right? And so now I've got this super high thing that's really thin. Well, let's just do it again. I just keep doing that forever, right? That's an impulse function, okay? And essentially, what it does is if you take that function, right, and you multiply it by some other function, and this is in 2D, we have a point now, this really tall, thin function. So what I'm going to do is take any old function here. This could be a picture of a brain. It could be a picture of Fourier, whatever. Any function here. I'm going to multiply it by that function, right? By that really tall function. After that multiplication, not much survives of f of x, right? Right? Of this function, most of this is zeros. So when I integrate across all space after doing that multiplication, what comes out is the value of f at 0, 0. That's the definition of a delta function. Okay. And so whenever you say, well, what is a delta function? You can explain it heuristically by saying this narrow thing, but that's the definition of the delta function. And it's used all over. It's used in signals and systems, and it's used in physics a lot, right? I'm not sure mathematically what its validity is, like measure theory and all that kind of stuff. Who knows? But it's very, very useful, right? And so that's the definition of a delta function. So here's some pictures of how you can use a delta function in different ways. The one we just looked at was one that had a non-zero value at the origin, and it got thinner and thinner, and it's just defined only at the origin, right? Well, if you add two more variables, right, as offsets, you can push that delta function to some other place in your image. Okay, so instead of just to the origin, now I'll put a delta function off in the corner, and I just do that by adding these two parameters, right, which is its position in the plane, right? I can take a whole set of delta functions, and I can just paint a line across my domain here, right, at which along that line is a whole set of delta functions, right? And so if I want to sift out just the values of f of x along this line, I can use this delta function to do that, right? And that's going to be an important concept in CT, because a lot of what we do in CT is look along lines through objects, right? And here's what you could call a sample comb. And so I have a whole set of delta functions, and they're evenly spaced on the 2D plane, and the distance between the delta functions is given by delta x and delta y. Okay, I can make these independent, but if I make these two the same distance, like that comb function or sampling function, I can make it a very dense sampling or a very loose sampling by changing that, right? So now if I multiply a function times this, it's going to sample that function at very discrete points, right, on the function. A couple of functions that are really important and come up all the time. This is just like putting tools in your tool shed. Is the rectangle function. And Dr. Liu is going to use this all the time. I'm going to use it. And it's a function that is 0 up until you get to minus a half. It goes to unity and then goes back down at a half. Okay, so it's just a top hat function of that distance. And that's called rect. Okay. And this is, I think in the book, they use this notation, but most of the time we'll just say rect. And then this is another function that's of tremendous value, and it's called the sinc function. And you can see it looks like one of those sombrero things, right? It has a peak of unity. It comes down, it has its first zero here, and then a negative peak, a positive peak, a negative peak, right? So it's like a kind of like a wavelet kind of thing. It has position in space, and then it's got this peak there. And you look at the formula for sinc, and it's a sine wave, right? Which is surprising to begin with. You go, wait a minute, sine wave, shouldn't that be zero at the origin? Like if I plug in x equals zero, sine, that's zero. Shouldn't it go through the origin? No, because there's an x under here, right? So this is going towards zero as sine is going towards zero. And eventually they're going towards zero at exactly the same rate. Because as you know, as you get closer and closer to the origin, sine becomes sine x is x. So that's why this is one in that limit, right? And then it just sort of follows the oscillations of sine as it moves out here, but it's decaying as 1 over x. And so it eventually just kind of disappears, right? So you've got something that's positioned nicely in space. Very, very useful function. And one of the reasons why, if we go like this, you can see what changed here, right? We put k in here instead of x. It turns out if you take the Fourier transform of this thing, right? So this is space, an x domain, you're in centimeters or whatever. This k is cycles per centimeter. That's what this function is. And this is the Fourier transform of that. So you take the Fourier transform of a rect function, you get this function. You take the Fourier transform of this, you get this function, right? So there are Fourier pairs. And in MR, it happens all the time, these Fourier pairs. Yeah. Because it is one of those things you do in like calculus. You say, well, does this thing have what's the limit of this as x goes to 0? And when you take that limit, it turns out to be 1. As opposed to, you can't just plug in 0 here, because when you plug in 0 here, you get infinity, and here you get 0, right? So in the limit as x goes to 0, it goes to 1. Okay. Now you can do these functions in 2 dimensions. Okay. So here we have the whole xy plane, and we just chunk off a unit square in the middle, center it up at 0, and that's the rect function in the 2D plane. If I take the Fourier transform of that, I get this, which is a sinc function in the 2D k-space or in cycles per centimeter. So it's got a central peak and then these waves coming out. Now, if you look at this, it's not a sombrero function, right? It doesn't have like equal waves all over the place. So it is the Fourier transform of this. Who knows what, if I gave you a function that had this central peak and then it had constant like circular waves going out of it, what do you think that corresponds to? Just using the symmetry. So if I had something that didn't change as a function of theta around here, right? So any radius I go out to, say this peak, I go around, it's a circle at that amplitude. So it doesn't change as I change my angle. What function over here doesn't change as you change your angle? It's a circle, right? So basically, we'll see that the Fourier transform of a circle gives you that sombrero function. The Fourier transform of this square thing gives you this, right? A lot of these symmetries work really well between Fourier space and the spatial domain. And that's because the Fourier transform, it's a linear mapping. So, yeah. Like a sombrero function, yeah.
Okay.
Yeah. We're going to quickly review complex numbers. And so These are used all the time in MR as well and in CT. So if I have a real and imaginary plane axes, I can describe a complex number with its real component plus J, physics people use I, times its imaginary component, right? And these numbers turn out to be exceedingly useful, and we'll see shortly why that is. So that's what the complex numbers looks like. It has a real part, imaginary part. Its length is just its length in the complex plane. That's simple Euclidean math to figure out what its length is. And its phase is this angle here. Okay, and so you can compute both of those. Here's some. So if J is defined as the square root of -1, J squared equals, -1. And then if you have another complex number such as 3 plus 2J, multiplication is just defined by doing the multiplication as you would any kind of algebraic multiplication. And you get, it can be a complex number, or it can be a real number. In this case, because these are complex conjugates, it's real number. So this is Euler's formula. This is often touted as the most beautiful formula in mathematics, right? Or in different ways of writing it. It's the most beautiful formula in mathematics. And this defines e to the j theta, where j, remember, is this, j squared is -1. And it's a phasor with unit length, and its position on the complex plane is given by cos theta plus j sine theta. Okay, this is true. It's not like when you look at this number, right? You say e to the j theta. What the heck is that in the first place? But so what's e? It's like the banker's number, right? It's 2.7186135. It's a transcendental number. It's just a number. But e to the x, when you take the derivative of e to the x, what do you get? E to the x, right? And you take the derivative of that, what do you get? E to the x, e to the x, e to the x, right? So it's a very special curve in that you look at the shape of that curve, and at any point on that curve, I can take an infinite number of derivatives and they'll always be the same value, right? That's kind of a weird curve, right, to start with. That's not like x squared, which you run out of derivatives eventually, right? So it's kind of cool. Cos and sine are kind of the same way, right? If I take the derivative of cos at any point along a cosine curve, I say, well, what's the curvature here? Like, what's the derivative or slope? Take the derivative. I get minus sine theta. Oh, okay. So I'll write that function down. Take the derivative of that, minus cos theta. Take the derivative of that, sine theta. And it just goes on and on and on and on, right? So they're infinitely differentiable. That's what's the thing tying e and cos together, I think, here, right? In many ways. So if you still don't believe it, then this is kind of the brute force way of understanding why this is true, okay? If you guys have done Taylor series, right? Taylor expansion around a point. And so when you do that, you just write out a function as an infinite series where there are various derivatives of the function of the coefficients, right? And so here, this is what cos x is. I'll just give that to you. There it is. It just keeps on going forever, right? It's x squared because cos is an even function, etc. This is what sine x is. And as you can see, when it gets really close to 0, sine x equals x. Off we go with these coefficients, right? If you write down this, if you just do the Taylor series of e to the jx and write it down, it looks like this, right? That makes sense because this is like e to the x, and that's what e to the x is, right? And so what we can do is just take this Taylor series, and I got a j squared in here. Well, that's going to be a -1. I got a j cubed in here. That's going to be a minus j. J to the 4th here, that's going to be 1. And just write that out, right? So now I write out that full Taylor series, and I gather up my terms that all have j's in them, right, on this thing, and I get this. So it's e to the j x is this plus this, and it's cos x plus j sine x. So it's kind of cool, right? That those, you never would have thought that something that's like a decay has so much in common with something that's totally derived by, circular arguments the way you do sine and cosine. But anyway, it's got something to do with the fact they're infinitely differentiable, I'm sure, but I don't know as much. Sorry for that aside. Okay. What we're going to look at a lot are plane waves. And sorry, this is really small, but here Sxy, okay, is this function, right? So where I've got sine of 2 pi and then an argument that has mu naught x plus mu naught y, okay, inside the unit square. And if I change this parameter, right, to 1, then I get basically a sine wave right here over one cycle. I don't change this parameter. I just leave it at 0. I get no change in amplitude as a function of y, right? It's just whatever it is at 0. And so that's a plane wave going in the x direction. And then if I up this coefficient here to 2, I get a plane wave again, but it has twice the frequency, 4, twice the frequency again. Now, if I change this to 1 here, the function still oscillates 4 times across here, but it oscillates once as I go this way, and I get what looks like a plane wave that's been rotated and it's going off in a different direction, right? So these are plane waves, and they're shooting off in different directions. As I change these two numbers in this formula, right, I can create these waves in different directions and different frequencies, okay? That's this function, right? We just looked at this function, and I can make these plane waves. However, I still have, if I only look at this, I've got a problem in that the value of this function at x equals 0, y equals 0 can only be 0, right? So if I want an arbitrary function in the plane, I need to also add an extra component to this. And so we have a cosine component to it, and we put it in the complex plane. And so now I have a phasor in the complex plane that has a real component and imaginary component that are both plane waves. And so now I can make values that are non-zero wherever I want, right? So that's how we're going to construct these phasors. And we're going to stop there and start there on Wednesday. Okay. Did that make it?
Thank you.
Sure. I think it made it.